Hello, hello. Well, okay, so today, or tonight, or whenever you're watching this, we are going to go over what my current project is. This project will change sporadically and without warning, but currently, we're trying to do a radio codec. One the military has been using, and then eventually, I believe they ended up trading out for something else eventually. But this is what I have. This is what I've been fanaticizing? No, hyper-focusing on for on and off the past several years, ever since I was like 16 to 18, I can't remember. Military Standard 188-110. The version C by the Department of Defense. Last standardized in January 2012. January 3rd, 2012. This standard, as you may be able to tell, 75 baud to 4800 baud. Capable of digital voice transfer, but also data transfer. Okay, correction, I believe in this case it's 75 bits per second to 4800, yes, bits per second rather than baud. But this waveform right here, always comes out at 2400 baud. This is my eventual goal, to create a program, as you may be able to tell, that creates this waveform. With any of these settings, minus frequency hopping mode, where it kind of takes a carrier frequency and switches between a bunch of them in order to avoid any interference in any particular one. I'm pretty sure that requires an actual radio setup. Something I don't have. I don't have a radio license, I don't have a radio. But I like radio, so I'm kind of stuck doing stuff like this. Not that that's a bad thing. I like it. It's fun. Phase shift keying, which is kind of like frequency modulation, except not. You got frequency modulation, where the frequency of a signal changes according to the input signal. Like, it shifts the carrier up and down in frequency rapidly with the change in audio voltage input. Typically using something called a voltage-controlled oscillator. So, adding voltage equals a higher frequency. Relative to the baseline carrier. And a lower voltage, or rather a negative voltage, gives you a lower carrier frequency than the baseline. And that's how you encode analog data. However, we're not working with analog data. We're working with digital. That's where you get frequency shift keying, where A change in the carrier frequency signifies a discrete change in the bits of a symbol. Basically, you have a different output frequency across the radio for a different combination of bits in the symbol. So, like, let's say it's a 4-bit. It's a 4-bit symbol. Okay. 4 bits. So that's 0, 0, 2, 4, 8, 5 to 15. So you need 16 discrete frequencies to transmit in order to transmit any particular combination of bits in a symbol. And there's a bunch of math to be like, okay, each one is this far apart in frequency, and that between that, the base carrier frequency, which there is no carrier, there's just kind of a center frequency attuned to, in this case at least. FM, AM, you have an actual carrier signal, like you have, let's say, an 88 megahertz sine wave just constantly being broadcast. In case of AM, you change how loud it is with the input audio. In FM, you change the frequency relative to the audio. FSK, you're not constantly transmitting that center frequency. You just tune to that frequency. And then the transmitted tones, kind of bursts of sine wave, correspond to each individual combination of bits. And yeah, there's a bunch of math to, like, correct errors, correct for fading that you might get over the radio, to correct for frequency drift, this and that. But in the end, discrete tones, discrete combinations of bits. Phase shift keying, it's a little different there. Instead of actually changing the discrete frequency, you go, okay, at time point 0, in order to, like, transmit a specific combination of bits in the symbol, you don't change the frequency, you change at what point in the wave you start transmitting, I guess. Basically, let's say the number 0, you start at the point in the wave. Like, if we... Oh, I don't have any drawing software or anything. Yes, I do. Hang on. No, I don't. I forgot to install GIMP. Yes, that might help. That might help a lot. See what happens when you aren't prepared. You have to wait. You have to be patient. What? Yes, here we go. Okay. Now, GIMP. Open up GIMP. Okay. Image, no, new. Why, yes. Okay. So now, can I actually switch to it? Can I do that? Yes, I can. Here we go. Okay. So, yes, okay. We're here. I'm not used to streaming, so seeing all the delay and stuff was kind of throwing me off. Anyway, so, what do we have? Much too large brush is what we have. Cat. So, that's not a straight line in any sense of the word. Oh, too far. What did I just do? There we go. Straight line. How do I draw a straight line here? No? Uh-oh. That's not what I wanted. Black. Yes. Straight line. Right here. Okay. So what do we know? With phase shift keying, you can have either the wave starts right on the center line, kind of goes up and down. Let's say that's a 0. Or we could start at the top of the wave and go. And let's say that's a 1. The frequency hasn't changed. But what you can have is 0, 1, and you have this big giant jump right here. Then you can have a 0 and a 0 and a 1. Gorgeous. Absolutely gorgeous. Yes. 100%. And the wave can look like this. The frequency hasn't changed. You just changed where in the ups and downs you are. And that's what tells you whether it's a 0 or a 1. Now, obviously, that doesn't mean that you can have like a 1 hertz bandwidth. No. Because these phase changes throw a whole bunch of like spectral noise, if that makes sense, into the signal. Basically, it'll, at least for the duration of the phase change, occupy extra bandwidth. And the faster these phase changes happen, the more bit data you need to shove through, whether that be by changing how fast the bit changes happen. Now, in this case, it's called binary phase shift key. You have two distinct phases to encode one bit. That's not always the case. You can have 4, 8, 16, 32, however much. But the more phases, not just how many more, not just how many more bits per second you shove through, but how many bits you encode in a single phase. Therefore, the more phases you have to shove through, the more bandwidth it'll end up consuming. Now, in the case of Military Standard 188-110, you have 2400 baud, but it ends up using 8 PSK, or 8 distinct phases. Basically, you have 8 different waveforms that you can transmit, each with a different starting point, and that ends up taking a total of 2.75 kilohertz of bandwidth in order to safely transmit this signal. But of course, you're not just taking the data, being like, okay, and 8 PSK is basically 3 bits per symbol. So each individual tone encodes a specific 3-bit value. Sort of. It gets a bit complicated. And basically, you do not shove the base data that you're trying to send. Be like, okay, every 3 bits, new symbol transfer. No, there's a lot of pre-processing involved, and that's not even taking into account the fact that it can transmit digital voice. Which before you can transmit the voice, you need to digitize it. And because you're doing it over the radio like this, you do not have a lot of room to send digital voice. So you have to compact that voice really small. And that's where we get into the purpose of what I'm doing at this very second in this stream, where I am currently focusing on the actual speech codec. A speech codec that there really isn't a lot of like documentation or anything that I've found about it. That's MELPe, Mixed Excitation Linear Prediction Enhanced. That is still under copyright, and not only is it under copyright, but the actual military standard is still classified. Unfortunately. That doesn't mean we're completely out of luck at all. No. It just means that the actual researching and everything else involved is a lot harder. And to be frank, I do not have the background knowledge for this. It is a very bad habit of mine to bite off projects bigger than I can chew. I'm working on it. Not in a very normal fashion, because I'm live streaming myself struggling with it instead of, like, going to school or any of this shit. Oh, my apologies. But I guess we're going with it. Okay. So, in this particular case, first of all, I'm not entirely sure how to say it. MELPe? Do I have to say MELPe? I'm probably not going to do that. I'm probably just going to call it MELPe. But it is classed as a vocoder. It is described by Military Standard 3005 and STANAG 4591. Specifically, I need the 2400 bit per second version. What I found was the 1200 bit per second version, which unfortunately means that I may be on my own trying to convert it over. But before we do that, first I gotta figure out how this stuff works. How do we figure out how this stuff works? By brute forcing our way through the code and dissecting it along the way. Because that's how I do things, apparently. Now, I got this code from this lovely GitHub repository, Rhizomatica. And they're doing something else pretty interesting with it, as far as I could tell. That is, if they have... They last touched it about 4 years ago, so, yeah. Peer-to-peer private talk over GSM FR. With a standalone MELPe encoder-decoder, which is right here. First problem. I've already built this code and tried to use it, and it doesn't seem to work. Yeah. Actually, can I, let's see if I can, like, show you guys. Okay, so, to test it out, I used the... Oh, God, where'd it go? There. Okay. I used the JFK space speech to Congress. Hopefully you guys will be able to hear it.
Space is open to us now, and our eagerness to share its meaning is not governed by the efforts of others. We go into space
I hope you can hear it,
because whatever mankind must undertake, free men...
Yes. Anyway, that was the goal. What I ended up getting out of that was this. Or rather, I can't even play it through the default Pop! OS audio player because it's not even encoded correctly. Okay, hang on. Oh, that's another... Oh, I forgot. That one's a app image, not an actual package. I don't know why they chose to do that. I prefer to just use APT whenever possible. I don't know why anyone else wouldn't. But I'm not an experienced programmer or any of that. I'm just me. Okay, so, where was I? Yes. JFK's space speech.
Space is open to us now, and our eagerness to share its meaning is not governed by the efforts of others. We go in...
Versus... I have to import it as raw data because, again, it's not encoded correctly for whatever reason. Yeah. No, I don't know why. It's, not pretty. But I guess that's just part of the fun now, isn't it? Just want to double check that I am in fact live here. Okay. Anyway, yes. So... yeah, I did figure out that. But in order to figure out that, I need to figure out what the code is doing in the first place. Do I know? Absolutely not, but I guess we're going to find out together. So, to start off with, here is the encoder, or rather the standalone encoder mean C file. Obviously you need strings and you need standard input-output. Can't have a functioning program without that. Or rather, a functioning, interactable program without that. Okay. Obviously, allocate pointers for the file you're taking in and the file you're putting out. Need a buffer for each frame and a buffer for resampled voice. Open up the input file, open up the output file. Note that I did change this. It used to just input, output, and then if either of these failed, it has failed. Instead, I split it up. Load the input file. If that failed, quit. Open up the output file. If that failed, make sure to close the input file, because it did open. It did not have that checked beforehand. Then we quit. Okay. And already here is where the fun begins, because now we have to initialize everything. We have to initialize the entire codec. In order to initialize the entire codec, you need to first take into account that MELPe, MELPe, is an analysis synthesis vocoder. You have to go through, you analyze what's coming in, and then you have to resynthesize it, and then you have a closed feedback loop going through to make sure that you're actually, like, doing it right. So first of all, you got the mode. This is something I've already tampered with because these used to just be define statements. That's cool and all, but that's very 2000. It is now 2020, midway through 2024. We have enums. You know, the thing that is designed to do stuff like this. So I swap that, this used to be a custom Boolean that. And then you add false. Which, like, nuh-uh. We have a Boolean library for that. So I figured I'd take the liberty to replace that. Now, I'm not sure that I actually took the liberty of... No, okay, I did. I went ahead and took the liberty of swapping every instance of this and every instance of this with this out of the actual Boolean library. So I don't need these anymore. Hopefully. Now, firstly, we've defined the Boolean type as assigned short. Not entirely sure what the purpose of that is yet, but I'm sure I'll find out here soon. I wonder if I can replace this. And pi. Yes? Yes. Yes, I can. Here we go. Beautiful. So we've got the software switches, analysis, synthesis, just analysis, just synthesis, and these I don't know. Not yet. Now, as far as I can tell, everything in here is hard-coded to 1200 bits per second. My eventual goal is to push it up to 2400 because that's what military standard 188-110 demands. Okay? Yes, I believe. Sampling frequency. 8,000 kilohertz. No. 8,000 hertz. Yes, 8,000 hertz, 8 kilohertz. 180 samples per frame, 3 frames in a block, for a total of 3 times 180 is... math. 18, 36, 540, I believe. Double check. Yes, 540. 540 samples per block. 512 samples is the length of the FFT, the fast Fourier transform. And the look ahead, well, a frame plus 110 samples. Pitch lag. Now, we are already running into the first set of interesting names. Pitchmax underscore Q7. Now, what I gathered, that means 7 quotient bits, basically. To define a number, you have, let's say 16 bits. Yes? Let's group them up into 8s. Okay. If you have 7 quotient bits, that means that the decimal point is implied to be not here, but 1, 2, 3, 4, 5, 6, right here. And because it's fixed point, it stays right there. This is the number 1 with a 7 quotient bits. Or, equivalently, it's 1, 2, 3, 4, 5, 6, 7. The number 128 in decimal if you didn't have that decimal point there. Because 1, 2, 4, 8, 16, 32, 64, 128. Which means that if you take this number times this number, you get this number. Or equivalently, zero, 1, 0, 1. You get that. 20480, or 20,480. That is maximum pitch lag times 128, or shift left 7, to free up 7 quotient bits, such that this right here, we get rid of all this right here is 0.5. This is 0.25. This is 0.125, and so on and so forth. Now, of course, we can't have real fun until we throw in the fact that you can have different sizes, different numbers of quotient bits. And you have to translate between them in order to do any amount of math. Because obviously, You can't just tell the computer, hey, take this. Take this quotient of 7 bits and divide it with, I don't know, 1.7 times hang on. That's 1, 1, and 12. 1, 2, 3, 4, 6, 7, 9, 10, 11, 12. Right there. Obviously, you can't just tell the computer, hey, divide these numbers. Because, first of all, these decimal points are implied. They are not contained within the, 16 bits that are the number itself. They are entirely implied. You have to keep track of them separately. Because, as far as the computer is aware, that's not the number. 160 with 7 quotient bits. That's the number 20,480. And this is not the number 1.7 with 12 quotient bits. As far as the computer is concerned, that is the number 6,963. So if you just multiply them or divide them or add them or subtract them as it is, you're not going to get the right answer. You're just going to get a bunch of garbage. Which, it would appear, is about half of all this code. Just going like, okay, we need to actually define how the fixed point math works, which a lot of it isn't even there. It's in here. It's in here. For anything else, you need the basic arithmetic. With saturation. You need the actual division. You need getters and setters. Rounding. All that stuff. Fun, right? Shift right, shift left. Both with and without a notion of the quotient bits, I do believe. No, this is 1632-bit. Fine. Okay. Got all of this math here. Up to 40 bits, because fun. Then you need to take into account how much bit shifting has happened. You need the logarithm, and for that you need the number of quotient bits. Which may or may not involve changing how many quotient bits there are in order to do the math correctly. Gotta interpolate and return a cubed 12. Gotta get the quotient bits for the anti-logarithm. You need the number of quotient bits for the squares and square roots and all that. And from all that, you need to then define matrix libraries, because if you're working with audio and speech, you're going to need a lot of matrices and vectors. And then you need fast Fourier transforms, real and complex. You've even got a specific fast Fourier transform subroutine for noise preprocessor. That includes its own initialization. Got the forward error corrector, digital signal processing, where you've got like the window functions, the IAR filters, all that fun stuff. All sorts of fun stuff. But I think I'm distracting myself. What we need out of this, first and foremost, we're initializing everything. I'll bring it back with another chunk. Hang on. I think I broke something. Oh, jeez. Oh. What the hell? Uh-oh. How do I fix that? Uh-oh. I don't know how long I've been just talking to myself. For 50 minutes. Oh, dear God. Well, apparently, this stream has been private. My apologies to everyone who has not actually been able to see anything. Okay, where were we? Alright. So, to recap, because I will not expect people to go back 49 minutes and 50 minutes and try and catch up. First and foremost, end goal is military standard 188-110. Specifically, 188-110C from January 3rd, 2012. But, before I can do that, I need to understand MELPe. Something that is technically still classified, but there are public, releases of it. And I got that. I got the version that I'm trying to work with right here. Rhizomatica. Now they're doing something cool on their own. As of 4 years ago. Peer-to-peer private talk over GSM. But they did include a standalone MELPe encoder. One that I haven't quite gotten to work yet, unfortunately. I don't entirely know what I'm doing here. But that's okay, because we're learning along the way, and that's fun. I've got it standing right in front of me. Right here. Got the encoder. Very basic. And we got a bunch of code from the 2000s and earlier, because fun. And I get the fun of trying to understand 24-year-old C code. And not only doing that, but trying to fix it, because when I tried to compile this as is, it didn't want to work. As I will now demonstrate. By going over and just a sec, I'm working on it. By trying to take JFK's space speech to Congress.
Space is open to us now, and our eagerness to share its meaning is not governed by the efforts of others.
But it turns out, as is, it comes out like this. Not very pleasant. No. I don't know what's happening here. But I guess we're gonna figure it out together, aren't we? First and foremost, mixed excitation linear prediction speech coder. Copyright 2000 Microsoft. Some of these files even have 1998 Texas Instruments, because I know they did a lot of help. And the extra fun is, I believe the 1200 bits per second is hard-coded, and I need to figure out how to make it 2400 bits per second, because That's what military standard 188-110 requires. It takes 2400 bit per second digital audio from this codec and transmits it as 2400 baud radio, phase shift keying, specifically 8-phase phase shift keying, plus or minus a little weirdness with how it handles the other bit rates and interleave lengths and all that. Now, what does that mean for me? Well, that means I'm basically learning all this from scratch. Because I don't really have background knowledge in all this. At best, I kind of know how to read C code. Or at least I'm capable of figuring it out eventually. Anyway, where were we? Yes. First, initialize everything. Clear up all of this. I can always open it back up on the way. Everything is fixed point, or yeah, fixed point. This is the SC1200 speech coder from Microsoft. And we're going to butcher it. Now, again, initialize. Set the mode, analysis synthesis, because it's a closed loop, it's a closed feedback loop codec. 1200 bits per second, with a frame size of 540 samples, I'm assuming. It's single byte words for the channel. They don't really tell you, like, yes, it's a number of bits, but I guess we're going to figure out what exactly that means together. We go 81 bits for this, 54 for this. Don't quote me too much, I'm kind of just making stuff up as I go. Frame sizes, number of bits. Then we initialize the analyzer. What does that involve? Well, got an input speech buffer here that we clear out for 360 plus 540, or 900 bits, or 900 elements. How big is it? How big is HP speech? 900 elements. You just zero the whole thing out. Yes. Now, this starts off 0, obviously, because this is the first time we run through any of this. We are... Now, the comments, or rather, all the function comments and all that look like this. I've been going through the process of making them actually Doxygen comments so that they look a bit more like this, and particularly so that we get all of these action. This looks a bit pretty, rather. Sorry. Okay. Waits for the Fourier harmonics. Got 10 harmonics. And we initialize them with the number 60 with 9 quotient bits. How does that work? How does this work? Well, that's a good point. Loop index, temp variable. Does this even matter? Does it? Because it's literally just the loop variables for the for loops, but it is being shoved into a register, it looks like. So I imagine that's an optimization, as well as this. Through here. That's... Yes, the weights for the Fourier harmonics, we just calculate them and shove them right in the global variable. Because this is, in fact, a global variable. Yes? It's supposed to be. Bleh. Yes, global variable right here, under global.c. With a quotient, with 14 quotient bits. So we initialize all that. We initialize their inverse. Then we set this flag so that we don't go through any of these loops again, because we don't need to. Now we initialize all the FFT pre-generated data, the real weights and the imaginary weights. And again, all this is fixed points, so you kind of have to custom define shifts, normalization, cosine, sine, addition, subtraction, all this fun stuff. And that's under mathlib, mathhalf, matlib for the matrices, FFT for the FFT stuff, digital signal processing. Yeah. Go through, initialize the FFT stuff. Then you start messing around with parameters like the pitch track. That gives you like the pitch for each note, correlation, cost function, in the class, whether it's voiced or unvoiced, energy, zero crossing, peakiness, autocorrelation, all that fun stuff. Now, again, I don't really know what all that means. I mean, I kind of get the idea of voiced versus unvoiced speech. I get the idea that peakiness is like the peak loudness, I believe. Zero crossing rate sounds pretty self-explanatory. Energy, less so. Autocorrelation, a lot less so. Pitch period, eh. Well, actually, I think that just goes back to pitch. But in order to do all that, you gotta initialize all that, fill it up with default data. That's interesting enough. Then we initialize the synthesizer. And this is where things get extra funky because, again, because it's a closed feedback loop, you have to deal with not only the current voice data you're trying to encode, but you're trying to, like, work in what you know about the previous stuff you've encoded. Like the previous frames, in order to properly correlate and compensate and encode this new frame. So you've got the previous set of parameters. You go through. We initialize the line spectral frequencies. Jitter. BPVC. BPVC. Now, when I look that up, I get boiler pressure vessel code, and obviously that's not it. PVC LPC. No, still not getting it. However, what that does mean is that first of all, I don't even know if this actually correctly converted to a public stream. Because, it started out as a private stream, and I think that might have broke things, because I didn't realize that it was set to a private stream. I thought it started out as a public stream, which is what I would have expected. Yeah. I'm just gonna, like... Yes, anyway, we go through. Oh my Christ, I don't know what's going on here. Anyway, line spectral frequencies. What are those? Line spectral frequencies are used to represent linear prediction coefficients for transmission over a channel. They have several properties, small, that make them superior to, like, direct transmission of the prediction coefficients. There's a lot of math here. I don't understand this math, but it's there. Uh oh, did I just... yeah. Okay, anyway. So we go through. And every loop, we add 2979 to the temp variable and shove it into an LSF in order to, initialize it. No jitter. BPVC. What does that mean? What a fantastic question. Because there are 5 frequency bands that they encompass. Let's see. Band pass voicing. Oh, band pass voicing coefficients. Here we go. And this is why I'm going through and looking through all the code, because these things have awful commenting that don't entirely explain what's going on. Caps lock. Band pass voice coefficients. I can't spell. Yeah, here we go. Here we go, much better. Spectral frequencies. Reverse that around. Okay. Pitch. Yeah. BPVC index. Band pass voice coefficient index. Yes. I believe that means jitter. Jitter? Index. Yes, maybe. Gain index. LSF index. FS index. Ratings. High efficient quantization of bandpass voicing coefficients for this superframe plays an important role in low bitrate speech coding algorithms based on mixed excitation linear prediction. That means things. Zim zim zalabim. Okay, anyway, bandpass voice coefficients. We clear them out. Synthesis begin. Sig save. Yes? What? Sig save. It's all the way up here at the top of the C file. I'm Not entirely sure what that means. Signature? Question mark? Anyway, we're gonna go back all the way down. Line spectral frequencies, sig save. I'm not entirely sure what that does yet, but I guess we're gonna find out here soon. FS mag. Fourier series magnitude, I'm going to assume. Filled with number 1 with a quotient of 13 bits. 10 harmonics. MSE. MSE. Whoa. Yes. Mean squared error. That sounds about right. Mean square error. Waiting. Fourier harmonics. Actually, we don't even go through this. Well, I don't know. The analysis initializer did that, I thought. Unless there are different copies of this. There are not. Okay. So yeah, we just skipped this because we already did this in the analysis initializer. Okay? We've initialized the analyzer and the synthesizer. Now, we go through and we start actually reading bits from the wave file. I hope that's what it's accepting, because otherwise I don't know, because there really isn't any documentation of that. And then, I guess we take that 540 samples of the wave file, and we start off by running it through a noise preprocessor before we do anything else. That's not what I wanted. You take that. No quotient bits. Because, well, it's a wave file. They don't have quotient bits. It's just an integer. Now, we take that. Obviously, this is our first frame. Here's where we spit out the processed file, or pre-processed. And I'm assuming this is an overlap window of some sort. Okay. We copy the speech bit, or bytes, or samples, and we copy them into our initial noise array. And we initialize the enhancement routine. Why we couldn't do that earlier? I don't know. Another optimized loop index, I'm pretty sure. Okay. Now, we take this initial array of samples, 256 samples, out of the 540. And we run it through a rectangular no, not quite. A 2-key window, right? two key window. The 2-key window. Tapered cosine. Yeah? Maybe? Yeah, a 2-key window with 256 sample window length. To 180 degree or point 1.8, 0.18, 180 degree. So 0.5 cosine fraction. Yes, maybe. Good question. It's a 2-key window. Two-key. Okay. Cosine tapered window. Oh! I know what I did wrong. I'm opening these up in the wrong window. Okay. 2-key window. 2-key. All the way down here. 2-key. Cosine tapered window. $256 samples. And in the code, it's 180, so 180 degrees. So it should be a cosine function of 0.5, right? I think. Could I understand this if I actually, sat down and researched it? Maybe, but I am absolutely addled with ADHD, so, good luck. Yes, anyway, so what do we know? Do we know anything at all? Perhaps not. But that's the fun part of learning. Okay, anyway. I'm going to throw stuff at the wall and say, yeah, that sounds about right. 0.5 cosine function, 256 sample, 2-key window. And I'm saying 2-key because that's what it looks about right. Because that's what looks about right. If you don't like it, well, I guess tell me about it. I don't know. There's lots of words that I thought were pronounced a certain way but actually weren't. And, yeah, I don't know. Yes, anyway. Run the first 256 samples through a 2-key window and just put it right back. Then we get to try and normalize it all. Okay, so that means we go through all those samples, find the biggest one, and then we find the normalization factor off that maximum one so that we can apply it to all the rest. Then you go through and we run an FFT all over it. A complex radix 2 fast Fourier transform, or all that input. Yeah. Lambda D. Lambda D. What does that mean? What does lambda D mean? It's not lambda dick. I don't even... That'd be cool, but... No. It's not cooperating with me. Hang on. Lambda D. No, not Amazon Web Services. Ugh. What does lambda D mean in reference to a speech codec? And what is with these weird names? Because, like, I understand. I wouldn't have called it zap, I would have just called it 0. But that's just me. The noise preprocessing FFT. This one on its own is already fascinating. Because we go through and just call the complex one. Guard. That's kind of how much the decimal point has shifted in the process, I'm assuming. I'm guessing. I'm assuming over here we're going through and like pre-butterflying the data to make it more efficient. Yeah. I don't even know. Check for overflow here. I think this is the very first actual butterfly calculation. So we go through 1, check for overflow, 3 butterflies just to kind of, for each n. And what is n? That was defined up here, wasn't it? And then I buff one that's direction. Yes. And its number of samples. $256, 512. You can go through, shuffle them around, check for overflow, kind of pre-calculate the first run through of the butterfly. From every 4 samples. Check for overflow. 2 more butterflies. And we just kind of keep going until we've gone through all 256 samples. Sure, push comes to shove, I'll have to actually go through and make sure even the FFTs are doing what they're supposed to, but like, the most amount of background knowledge I have is reading C code, so yeah. Again, lambda D. Mean squared error. I think, pretty sure. That's what it sounds like. Just kind of looking at this. That's Fourier transform. Each sample, you square it, divide by 2. Skip the next one. Then it looks like you do this with the midpoint. 256, 514, just a couple samples less than midpoint. You square it, divide by 2. And then you go back and do everything in between. Square it. Add the square to the next one. 5 by 2. Then you go all the way back, sum it through, and, or rather, not sum it through, but iterate through, and find its max, and then create a normalization value from that. Then you go through and normalize everything you did up here, and then just take the high half of that and put it right back into the FFT buffer. And then from here, the a shift, which is basically how far away from 15 quotient bits I believe it was. Yes. How far away from the 15, from having 15 quotient bits you are. Plus the guard shift, or rather the number of quotient bit change, I guess, from the FFT. And then you shift that left by the actual new normalization value plus 7. Okay. So you toss it to the frequency domain. Lambda D lambda underscore D? Is that what it means? No. Maybe? There's optics. That's not what I'm looking for, am I? D. E. Lambda D. Lambda D. Explain. Explain! Wow! Anyway, no. Angular resolution seems to be the common search result. The coder. Lambda D. Lambda D. Not very explained. Okay. D. No. D. Speech coding. Yeah, I don't know. It means something. I know that much. Lambda D. Don't even know. And now I'm lost. Oh, there we go. Okay. Peak value out of that. And anything that looks like this with the capital L in it is a 32-bit function, not 16, as far as I've gathered. Now here's the interesting part. Correlation domain? I'm guessing that's basically frequency at one dimension and correlation at the other. Yes, because we are in fact in the frequency domain. I'm not entirely sure what's happening here. Because we go through window length, or frame length, 256, 258 times, let's say 0 plus 2 is 2. No, hang on. 256 plus 0 plus 2 is 258. 256 minus 0 minus 2 is 254. Okay. $256 plus 4 is 260. Is equal to y above 56 5432. Okay. Then we go through each and every last one of them. Y above 56 minus 0. 254, 255 is equal to negative y buff 256. 54 plus 1 is 5, 256. No, hang on. 56 plus 0 plus 3, so that's 9. Is equal to 256 minus 0, 254, 255. Then y buff 256, 7, 8, 9, 10, 11. $256, 5, 4, 3, 2, 3. Okay. Correlation domain. Then, once it's in the correlation domain, do we run a reverse FFT on it? And adjust normalization factors and all that. And copy it back to the initial noise vector. Then we go back, find its maximum for normalization purposes. And shift it. And then we run, I believe, a partisan window. Yes. A partisan window I think I just closed that. A parts and window. Yes. Anyway. Then we go through. Once it's all normalized and all that. And smooth. We go back and convert it back to the frequency domain. And we go through and get a good estimate of lambda d. What does lambda d mean? Still not sure yet. But I know it's there. Lambda d. Lambda. A perfect way to smooth your noisy data from towardsdatascience.com, which is a Medium product, which means it's probably going to annoy me about the fact that I don't have an account, but I don't care. Smoothing. Interpolation. Configuration. I don't know. Unsure. But we're doing a lot of math here. Sum is equal to 181 times. Oh, I already summarized that below. Shift is the normalization of that. Or the normalization factor. Okay. Lambda d 0 is equal to MSB of some left shift the normalization factor. Yes. Then we have a separate array for the new normalization factor. And we take this L sum right shift equals 8. Okay. Then Okay. Plus 2. Okay, then we normalize that one. Lambda d 128 is equal to this okay, lambda d is some, or rather, data left shift, then extract the highest. Okay, well. So, I'm guessing this is the sum of error. Maybe? Question mark? Oh, some. Because again, there really isn't all that much commenting here. Okay, normalization shift amount. Data with shift. Extract the high bits. Wow. One shift plus minus shift lambda d is equal to MSB okay, wow. go through and do the same thing until we've gone through all the window. Okay, well, go through, and the final normalization factor. In power. Okay. Long-term SNR. Heading window. Initialization of variables for minimum statistics noise estimation. Okay, well, I think my body is telling me to pack it up for today. So, in that vein, good night. Enjoy yourselves. If you know what you're looking at, I could definitely use the help. If you don't know what you're looking at, hopefully at some point in the future I can help you understand. Because at this point, I'm where you're at. But that's what's fun. We're learning things. But, enjoy yourselves. Have a fantastic night, or day, or whatever time it is where you are when you're watching this. And... Tschüss, auf Wiedersehen, Wiederpeivan. Have a great night.